Hey everybody, as base 10 numerals, this computation is not valid. Now most time we talk base 10 every day, we have 10 digits on our fingers, but let's write the subscript 10 right here. So 403 base 10 times 205 base 10 does not equal to this 414? And that's really quick check, isn't it, ladies and gentlemen? Because notice that 3 times 5 would indicate this product ends in the digit 5, and this product ends in the digit 4. So this cannot be true in base 10, okay? Now, how about another base? Is it possible there's another base where this computation might be accurate? It might be true, okay? So here we go. Let's do a check on this and let's write down what it means, or I'll do that for you. If you come down, folks, 403 base b would be 4b squared plus 3. Notice that the 0 placeholder, we leave out the power of 10 right here, okay? Or we leave out b, the value b. In a similar fashion right here, we have 2b squared plus 5. Again, the 0 means a missing b term, okay? In a similar fashion, and y'all, you may have noticed with any base, it's always 1 power lower, okay? It's the 4th power because you have to allow for the units position right here, okay? It is a 5-digit number, but the highest power is going to be a 4, and that's consistent with base 10 or any other base, okay? And so we're trying to find out, is there a b such that this computation holds, and we're about to find out. Now, you can see some nice things happen right here, folks. When you expand this out, the 8b to the 4th terms are going to cancel. Well, that was by design, just to make the computation, or make it work actually. All right, and now I won't bore you with all the algebra, but what happens right here, when you collect like terms and write it as a polynomial in the variable b, you end up with 2b cubed minus 22b squared and I got plus b minus 11 equals 0. Okay, and folks, again, these terms cancel out nicely, and I'm pretty sure I got this right here. Here's the 2b cubed, and then you can see that the 26 minus 4 bring it to the other side, gives you minus 22b squared, plus b minus 11 equals to 0. Now notice there's some candidate b's right here. There's something called the rational zero theorem, which tells us that the possible rational zeros, and I'll write this down, potential rational zeros I'll just call them potential, folks, and then they are 11, 1, and I'm going to not, there's plus and minus versions too, but you have 11 over 2 and 1 over 2. Again, that's called the rational zero theorem, and it's a consequence of taking all possible divisors of the constant term, put that in the numerator, all possible divisors of the leading coefficient, put that in the denominator, all right? Now, and I should be writing plus or minus in front of all this, okay? Now, there's nothing that precludes the 1/2 or a fraction being a base. That's okay, and even you can have negative bases. Dr. Barker talked about negative bases all the time, but it turns out the one that works, and I'm going to go ahead and cut to the chase, is 11, and let me verify that for you. I'm going to use something called synthetic division. But notice you would have, what here, 8 checks, okay? Now, so let's do 11, and then what I'm going to do next here, folks, this is a very familiar process that's called synthetic division. Write down the coefficients of the cubic polynomial, 2 minus 22. And then there's an understood 1 in front of here, right? So we'll put 1 there, and then negative 11. Okay, now, so again, the standard process here is you bring this 2 down, and you multiply 2 times 11, you get 22. All right. Okay, and then that gives you 0 right here. And then 2 times 0, 11 times 0 is 0, add, you get 1. And then finally 11 times 1 is 11, and you get 0. So you see you get 0, so it does evaluate to 0 right here. Okay, and then what would this be? 2 cubed, right, I guess. What would this be, folks? This would be the same thing as 2b squared minus 1, I think, right? Is that right? Yeah, maybe. But anyway, we do get that 11 is a 0. Okay, so 11 is the answer. So our b is definitely equal to 11. Now you get the other two, I think, end up being irrational or imaginary numbers. Okay, and that's not too hard to believe. If you look at this and set it equal to 0, don't you get? Yeah, you get. Does that work out? I may have this backwards here, but in any event, 11 is the only one that works. Okay, so base 11 is the only one. I haven't quite shown you, but it turns out this is a cubic with 1 real solution and then 2 imaginary solutions here. So did I get? Yeah, but I think we're in pretty good shape here too. Did I leave out? I may have left out something here, but in any event, 11 is the proper base here for the computation to hold. So it's b is equal to 11. And it is possible for these problems to have more than one answer, but this is not one of them. I haven't convincingly showed you that. But you could have 2 possible bases in quadratic cases and maybe cubic cases too. I'm not sure. But b equals 11, and you can carry out the computation to verify. But pretty sure I got this right. Okay. Thanks for viewing.